Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about bomb calorimetry. And bomb calorimetry is so similar to what we've been doing in the last couple videos with a coffee cup calorimetry. There's plenty of similarities, but we're going to talk about the differences as well. Okay, so the way bomb calorimetry works differently than coffee cup calorimetry is in coffee cup calorimetry, we just pour our reactants into our coffee cup, and the heat flow, if this is exothermic, which it is, okay, the heat flow leaves the chemical reaction and goes into the solution only, okay? The way bomb calorimetry works is it's almost always exothermic, so we're blowing things up inside of this bomb calorimeter, so we have this chemical reaction inside the bomb calorimeter, but the heat flow is going to a lot of different places because there's a lot of stuff that's inside a bomb calorimeter that is not inside a coffee cup calorimeter. Now, the only similarity is that there's a thermometer in each, but the bomb calorimeter has a stir that stirs the solution. There's these probes that go inside, and these probes send an electrical signal, and that's what makes the explosion occur. So there's all this other stuff that's in the bomb calorimeter, okay? So the way it works is that the bomb calorimeter is going to use heat capacity, where in coffee cup calorimetry, they're using specific heat, okay? So a bomb calorimeter is going to use something called heat capacity, which is capital C, versus little c, which is specific heat. And I do have a video about 3 videos ago that talks about the difference between specific heat and heat capacity. And we're going to touch it slightly here. If you want more details, you'll have to go back into that video. So normally when we do calorimetry, we use this Q equals mc delta T equation, okay? Well, heat capacity is just the multiplication of mass in specific heat. So really, we're doing the same thing. We're just subbing out mass and specific heat for heat capacity. So the equation simply becomes big C times delta T instead of M times little c. So if you're good at coffee cup calorimetry, it's just a small jump to get in to be able to do bomb calorimetry. So let's go ahead and jump into our problem, okay? If you want to pause the video right here so you can look at the prompt a little bit more carefully, you can. But when you unpause it, I'll be working on the problem. And what I'm going to do is I'm going to just start setting up this particular problem, okay? So the first thing it tells us is that the heat capacity of this calorimeter is going to be 4.812 kilojoules per degree Celsius. So as this calorimeter heats up a degree Celsius, that means it's absorbing 4.812 kilojoules. If it absorbs 2 degrees Celsius, it would be 2 chunks of the 4.812. Okay? So inside this calorimeter, we're going to explode some lactic acid, and it tells us that we're going to explode 0.5865 grams of this lactic acid, which has a formula of HC3H5O3. That's the formula for lactic acid. Now, this bomb calorimeter has an initial temperature of 23.10 degrees Celsius and a final temperature of 24.95 degrees Celsius. So I think I have all the information that I need from the prompt up on the board at this time, okay? So what I'm going to do is figure out how much heat is being absorbed by this calorimeter, okay? Well, the calorimeter has a heat capacity of 4.812 kilojoules per degree Celsius, and I got to figure out the temperature change. So 24.95 minus 23.10 is going to be 1.85 degrees Celsius. And what I'm going to do is I'm just going to multiply these two numbers to figure out how much heat is being absorbed by the calorimeter, okay? And when I do that, the number comes out to be 8.90 kilojoules, okay? Now that heat is actually going in from the chemical reaction. It's going into all of these places, and the thermometer is just measuring the calorimeter as a whole, okay? And for each degree Celsius that it goes up, that means it's absorbed 4.812 kilojoules, okay? Well, if it goes up 1.85 degrees Celsius, that means the calorimeter absorbed 8.90 kilojoules, okay? Well, where did that energy come from? It came from the chemical reaction. So if this Q is how much heat is being absorbed by the calorimeter, then the chemical reaction is going to be giving off the same amount of heat, but opposite in sign. So if it absorbs 8.90, that means the chemical reaction gave off 8.90 kilojoules, okay? Now, that's for this amount of lactic acid. And the prompt says, what is the enthalpy change per gram and per mole? Okay, so the first thing that I want to do if I want to figure out the enthalpy change of this chemical reaction on a per gram basis, I'm going to take this negative 8.90 kilojoules and I'm going to divide it by how many grams I have, 0.589565, sorry, 0.5865 grams. And if you divide these two numbers on a per gram basis, this means that it's given off negative 15.2 kilojoules per gram. Now the prompt also says, what is the enthalpy change on a per mole basis? So I'm going to come back over here and I'm going to find the enthalpy change for the chemical reaction on a per mole basis. So I'm going to take that same heat, negative 8.90 kilojoules, and I'm going to divide it by the moles. Okay, well, I need to do the molar mass here, okay, and calculate this. So grams to moles, if I add up 6 hydrogens, 3 carbons, and 3 oxygens, I find out that that's 90 grams per mole. And the amount of moles that would be equal to is 0.00652 moles. I'm going to take that number, 0.00652 moles, and that's going to tell me my enthalpy change per mole. Okay, and if I do that calculation in my calculator, I find out that it's negative 1,366 kilojoules on a per mole basis. Okay, so as you can see, the bomb calorimeter problem works almost identically to the coffee cup calorimeter problem, which I'll run through really quickly here. In this problem, we poured the two things together. There's 100 grams total here, so I'm going to take Q equals MC delta T instead of heat capacity. So once again, the only difference is I'm substituting mass and specific heat for this topic called heat capacity. And I'm basically figuring out how much heat is absorbed by the solution, okay? And then I make it the opposite, just like I did here. I found out what was the heat absorbed by the calorimeter, and the chemical reaction is the opposite of that. And then I can put it on a per gram or per mole basis. In this problem, we put it on a per mole basis by figuring out how many moles of hydrochloric acid was actually reacted in the coffee cup calorimetry. So once again, the major difference between bomb calorimetry and coffee cup calorimetry is that coffee cup calorimetry uses the mass of the water and the specific heat of the water or solution, where bomb calorimetry substitutes out the mass and the specific heat for heat capacity. But other than that, they're very, very similar, okay? And they work out exactly in the same manner. So if you found this content helpful, please give it a like and subscribe, and even leaving a comment will really push this information out to other students that are interested in learning chemistry.